Hey guys, today we're going to talk about subatomic particles and average atomic mass and do some calculations, okay? So let's jump right into this. Now I'll probably have to move my face around a little bit, but hopefully we'll be good to go. So let me grab my pen, make sure this is working. Yep, okay, good. All right, so subatomics. A little bit of review from last week. Number one, this is the Bohr model of the atom. We know that because we have these lovely orbits right here, right? That tells us it's the Bohr model of the atom. Notice that in the nucleus, right, we have our protons and our neutrons, right? That's where they reside. And for the point of this model, the electrons are in the orbit. So we're going to see these drawings kind of commonly, we'll say. It's okay to think about the atom in terms of the Bohr model. It simplifies it and makes it worthwhile, okay? So that would be a little bit of review from last time. A couple other things we want to make sure we have down, especially with what we're going to talk about today. We need to know the definition of an isotope. That's an element that has, or versions of an element, sorry, that have different number of neutrons in the nucleus. Two different ways we can show an isotope. We can use hyphen notation, all right, or we can use nuclear notation. And the difference in the two is literally the hyphen, right? So hyphen notation, you have some element name and then a mass number. Like right here, we have carbon 12. And then nuclear notation, we have the symbol and the mass number over top of the atomic number. Now, I would still read this. I would say, hey, this is still carbon 12. That's what we would say out loud. But the nuclear notation is a little bit more useful. And in the last video, we also worked on identifying the subatomic particles present based on either hyphen notation or nuclear notation. We know that it's a little easier with nuclear to find neutrons because we're just going to subtract. Remember that this is my mass number, this is my atomic number, and so if I want to find neutrons, I would just subtract the two. So this would be 26 neutrons. I know it's neutral, so it must have 48 electrons, and it would have 48 protons, right? We also know that if we have hyphen notation, we have to look up the protons. So look up the proton number on the periodic table of the elements, right? So that was last video. A couple things that are we should be good at. We're going to talk more about isotopes today. So let's look at that. What is an isotope to chemistry? So something you may have noticed on your periodic table is this average atomic mass. It's this number at the bottom of the element tile, and it is what we use in order to describe an element as far as its atomic mass is concerned. But here's the thing. Since I have some isotopes that weigh X and I have some other isotopes that weigh Y, how can I give an accurate measurement for krypton if I don't account for the fact that there is, say, a greater percentage of X in the universe compared to that Y isotope? So in order to do that, the average atomic mass is actually a weighted average of the different isotopes based on what we call their percent abundance. So a weighted average works like this. It takes into account the overall percentage of what exists in order to weight certain isotopes greater than other isotopes. So it's a lot like a grade book in a classroom. So if you're working on this, this grade book setup right here, then you don't do a homework. Well, okay, homework's only worth 10% of your grade under this little illustration we have here. But on the other hand, if you're like, you know what, I don't think I'm going to do a test this week, I'm just going to skip it and take a 0, well, that's going to have a much greater impact on your grade because the test, the summative assignment, right, is worth 60% of the grade. So this is kind of similar. If you have an element that has three isotopes, one is 60% abundant, one's 30, and one's 10, well, then the 10% abundant isotope should probably not impact the overall weight or mass, rather, of the element. On the other hand, the 60% is definitely going to impact it. So we would expect the isotope to be closer to the greater abundant isotope. But before we get to isotopes, we got to talk about these moles, right? Because if we go back here, there it is right there, we say that carbon is closer to 12 grams per mole, right? If you look at carbon on the periodic table, it's probably going to say something like this underneath of it. And so this is closer to 12 than 13. There is carbon 13, there is carbon 14 isotopes that exist, but carbon 12 is by far the most abundant. And when we report this, we usually talk about it in terms of grams per mole. Now, we've talked about grams. We know what grams are, but a mole, that's new. So here's a mole. A mole is a unit we use in chemistry to measure a specific quantity of matter. All right. We use Avogadro's number in order to express the mole. And what a mole allows us to do is compare apples to apples. All right. If I have one atom of carbon and I want to compare that to one atom of oxygen, well, they're different atoms, so they're kind of hard to compare. On the other hand, if I have plus, that's a really small number of atoms, right? It would be really hard to compare the properties of just one atom. But on the other hand, if I want to compare, say, a pile, right, a big gas cloud, maybe a compressed cylinder of oxygen, to a bunch of carbon in a pencil, like graphite, well, that would also be difficult because they have different properties and they're hard to measure those differences. So what we do in order to get them in common terms is we always make sure that we're comparing the same amount of atoms. And we do that with the mole. So a mole is the same number of atoms. So if I have 1 mole of carbon and I have a 1 mole of oxygen, then in both of those piles, I have 6.022 times 10 to the 23rd atoms. Now that's a really big number, right? 6.022 with 20 zeros after it. That's a lot of atoms. Atoms are really small. And because you may be familiar with scientific notation, but not on such a grand scale, I've included these 2 videos. Click on them, pause me, go watch them. You can look them up on YouTube. It's just called Powers of 10. The Morgan Freeman one is newer, but I like the IBM one. It's like from the 70s. It's pretty cool, but it's the same video. Basically, it just zooms you out from the planet in meters in powers of 10. So go watch that and then come back and we'll keep going. So Avogadro's number, 6.022 times 10 to the 23rd atoms is in a mole. The reason I kind of left this blank here is actually we could write particles right here. And what I mean by that is depending on what you're talking about, the atom or whatever this unit is going to be may change. To be totally true, if you add 6.022 times 10 to the 23rd horses, you would have a mole of horses. A mole is just that number of any discrete thing. The difference is, let's say I wanted to talk about water, right? Here's water. It's H2O, right? It's got our lone pairs on top. Well, this is a molecule. So if I want to talk about a mole of water, 1 mole of H2O, well, then actually I have 6.022 times 10 to the 23rd molecules. Because the discrete unit of water is a molecule, not an atom. So we say particles, just individual discrete things. Now, you just watched that video. Obviously, times 10 to the 23rd is huge. So a mole of carbon only weighs like 12 grams. So that implies to us atoms must be really small. Just to kind of give you a visual, right? If you had an atom and an atom was a meter across, and you had a mole of them, well, that mole would stretch from one end of the observable universe to the other. All right. Fortunately for us, atoms are really tiny, so they don't take up a lot of space at all. The big takeaway, all right? The mole lets us compare the same number of atoms in order to compare to 2 different elements. Oxygen and carbon, apples to oranges, right? They're not the same thing, but a mole of each lets us compare them. Now, back to the isotopes and the percent abundance and the weighted average. How do these things come into play? Well, the average atomic mass is a weighted average that's going to account for our percent abundance of an isotope. There is no division when you're finding a weighted average. Okay, we're going to multiply, and then we're going to add up the results. Okay, that's really important. Big common mistake I see kids make. They want to divide because they see the word average. And when they see the word average, they think, oh, we add them all up and divide by the population, right? We divide by how many numbers there are. Okay, that's true. That is how you find an average. It's not how you find a weighted average. So we're going to multiply, and then we're going to add. That's going to give us our answers. So let's look at one of these. Copper exists as a combination of 69.15% copper 63 and 30.85% copper 65. What's its average atomic mass? So we have two isotopes of copper. We need to come up with a weighted average that adequately describes a sample of copper in real life. What would it probably weigh if we had a mole of copper? So the first thing we want to do is we want to look at these percentages right here. We want to convert those percentages to decimals. They're going to add up to the number 1. So hopefully you know that in order to convert a percent to a decimal, you move the decimal 2 places to the left. In other words, you're going to divide by 100. So 69.15, move it 2 places to the left, we get 0.6915. We do the same thing with 30, and these are our percent abundances converted to a decimal. Now, once we have those mass numbers, once we have those decimals, we're going to multiply it by the mass number. So when we say the associated mass number, here's what we're talking about. 69.15 goes with copper 63, and we'll circle this one. 30.85 goes with copper 65. So we're going to multiply 63 times 0.6915 because they go together. And we're going to multiply 65, all right, times 0.3085. Right there. They go together. And this is going to account for the fact that only about 30% of a sample is likely to be carbon-65. And it also accounts for the fact that about 69% of a sample is going to be copper-63. So let me get rid of some of these annotations. There we go. So we've multiplied them, and we're going to get 2 products. Once we get the products, we're going to add them together. And there it is. Copper, 63.617 grams per mole. That's its average atomic mass. Let's try another one. Chlorine exists as 75.77% chlorine-35 and 24.23% chlorine-37. Calculate the average atomic mass. Well, take a minute, pause me, see if you can do it. Then we'll go through it, all right? So the first thing I want to do is I want to convert my percents to decimals. So I divide by 100 or move the decimal 2 places to the left. Then I want to multiply the mass number times the decimal. That's going to give me 2 products. I want to add those products together, and my average atomic mass should be 35.4846 grams per mole. Pretty easy, okay? Now, not every single compound only has 2 isotopes. Some have many more. So let's look at silicon. Calculate the average atomic mass of silicon. There are 3 isotopes. Silicon-28 at 92.2297%, silicon-29 at 4.6832%, and silicon-30 at 3.0872%. Well, nothing changes. I just have one extra step. I'm still going to do percent to decimal, decimal times the mass number, add the products. So take a minute, see if you can do it yourself, hit pause, and then we'll go through it together. So, convert your percents to decimals. Move the decimal to the left 2 places. Now, notice something. When I go 2 places to the left here, I have to add a 0. All right, very important. 2 places to the left here, I had to add a 0. Very important. All right, if you mess that up, the way you'll check yourself is, remember, these numbers are supposed to add up and equal 1.00. If they don't, you know you did something wrong. Then I want to multiply the mass numbers times their decimal counterparts. Pretty simple. And then I want to add those numbers together. Add your products. 28.11 grams per mole. Here's another one for you. All right, the only way we get good at this is practice. So, do another one. Gallium has 2 naturally occurring isotopes. The mass of gallium-69 is 108% abundant, and gallium-71 is 39.892% abundant. Find the relative atomic mass of gallium. Little note, relative atomic mass, average atomic mass, those words are interchangeable. So convert your percent to decimal. Remember, if you need to pause it and work it yourself, do so first. But convert your percents to decimals, divide by 100, right? Move the decimal 2 places to the left. Multiply the mass numbers and their decimal counterparts. Add the products, and we get an answer. So those are pretty easy, okay? We can do this. Here's one more, right? There's always one more. Calculate the average atomic mass of lead. The 4 lead isotopes have atomic masses and relative abundances of, and then it lists them. This is a pretty common way you'll see it on a test. Just know that these two go together, this one and this one go together, these two go together, and that one goes together. Pause it, give it a shot. Remember, convert to decimal first. So here we go. Convert to decimals. Well, here's another good one for you, right? 1, 2, make sure you add a 0. That'll mess you up. You can check your work. Make sure these add up to 1. Multiply your max numbers and your decimals. Add your products. There we are. All right, so far all we've done is find average atomic mass. Let's find percent abundance, all right? You don't really know a math problem until you can work it both ways. So let's look at this problem. It says, bromine has 2 naturally occurring isotopes. Bromine-79 is 50.69% abundant. The relative atomic mass of bromine is 79.904 grams per mole. What is the percent abundance of bromine-81? All right, so we're going to work this backwards. In order to do that, we need to use an equation. So what do we know from the problem? First, we know the answer that we've been looking for in the last couple ones, right? We know the relative atomic mass of bromine. So it is equal to the sum of the products, all right, of the percent converted to a decimal and the mass numbers. So let's just fill that in as an equation. So where did I get this stuff from? Well, the x is the missing percent, and it's going to be in decimal form, okay? Now that I have this, I can just solve it like a regular algebra problem, right? I have 81 times x, well, that's 81x. I have 79 times 0.5069, that's going to give me a product. I then subtract and divide, and I'll be good to go. So combine like terms, right? Simplify. 79 times 0.5 is going to give you about 40. Subtract the 40 from both sides. It's going to give me a new equation, 39.8589 equals 81x. Divide by 81 to get x by itself. And there is my decimal my percent as a decimal. So multiply by 100 to get it back to a percent. Now, let me point out where I got some of these things, right? First, this 79 right here is that 79. So I know bromine 79 is 50.69% abundant. Well, that's this whole bracket right there. I'm looking for the percent abundance of bromine 81. So 81's right there. The thing that says, what is the percent abundance? Well, that's the thing I don't know, so that's x. I know the relative atomic mass is in grams per mole right there. So that's where I got everything from my problem. Try another one. Antimony has 2 naturally occurring isotopes. The mass of antimony 121 is 120.904 AMU, and the mass of antimony 123 is 122.904 AMU. An AMU is an atomic mass atomic mass unit. Using the average mass from the periodic table, find the abundance for each isotope. Well, so the first thing I need to do is I need to look on the periodic table to find out what antimony normally is. Antimony is Sb, by the way, on the periodic table. So I'm going to write the same formula I did last time. Now take a minute and see if you can figure out how to do this on your own. Now I'll give you a hint. You've got 2% abundances. You don't know either of them. So call one of them X and then figure out how to get the other one. And there's a hint. They must add up to 1. So take a minute and then we'll go through it. All right, here's my algebraic formula. I looked up on the periodic table and found that the average atomic mass of antimony is 121.760. That's going to equal the sum of the products of the mass number times the decimal percent, right? Math's a language. We've got to be able to describe these things. The only problem is, in the equation, it didn't give me any of those wonderful decimal percents. It gave me the answer of the multiplication. So I've got to plug these things in. So I used x and 1 minus x for my two decimals because they have to add up to 1. So 1 minus x is going to be x, right? The next thing I want to do is I want to solve for x. So it's just like you're walking into algebra class. So I'm going to put these things together, all right? There we go. Combine your like terms. That's x in red. That's x in blue. Divide by -2. And I get my decimal, 0.572. Now, 0.572 is one of the x's, right? We need to convert that to a percent. It's the x that I looked for first, okay? Now, since I know 0.572 is the 1 percentage, right, that's going to become 57.2. The other one has to add up to 100%. So antimony 123 must be 42.8%. That's a tough question, all right? Just takes a little thinking. Now, as you're working these, please remember, use a calculator, all right? Use your scratch work, write them down. This last problem, really tough one, all right? This would be like a challenge question. But the other ones you can definitely expect to see on a test or a quiz. Now, as you're working these, make sure that if you have questions, all right, you let me know. I can't help you if you don't ask, all right?